This video lecture deals with the very important concept of vector components. I'll begin with a discussion of how one determines the so-called x component of a vector. I show a vector pointing into the first quadrant of an xy coordinate system. Call that vector A. The vector makes an angle theta with respect to the x-axis. I equally well could have decided to indicate the angular orientation of this vector by specifying the angle it makes with respect to the positive y-axis. It's quite arbitrary. To determine the x component, or any component of a vector for that matter, imagine that the vector itself is a hypotenuse of a right triangle. I'll sketch one of the two possible right triangles now. I drop a line down from the tip of the arrow until it intersects the x-axis at an angle of 90 degrees. The leg of this right triangle is that vertical broken line. The base of the right triangle I'll sketch now. The arrow can be imagined to cast a shadow on the x-axis if a light is placed above the vector A. It casts a shadow indicated by the broken red line that points in the positive x direction. Because that baseline points in the positive x direction, has a shadow that points that way, we indicate that the x component of that vector is positive. Now, the width of that base can be found using SOHCAHTOA. That base is the side that's adjacent to the angle theta, and therefore it's the cosine trig function that's operational. And so we can indicate that the x component, which will symbolize this way, a subscript x, is equal to the hypotenuse times the cosine of theta. But the hypotenuse has a length that's symbolized as a. And so we have a sub x equals a cosine theta. What I'll next show is how to calculate the x component of a vector that points into the second quadrant. Here is a vector that points into the second quadrant. Its length is symbolized as b. I choose to indicate the orientation of this vector by showing the angle the b vector makes with respect to the negative x-axis. It's called theta. The first step in determining the components of a vector is to make sure that the vector in question has its tail attached to the origin of the xy coordinate system. That's what we did with this first component calculation. I show once again an xy coordinate system, but just the second quadrant. It's the only portion of the xy coordinate axes that are relevant to us. The tail of the b vector is attached to the origin. And I've already described the theta and the value of b as being the angle of orientation and the magnitude or length of the vector. After you visualize or place the vector in question, attach its tail to the origin, you then construct a right triangle whose hypotenuse is the vector itself, already in position. And so here we go. To construct the right triangle, I'll drop this line straight down. That's the leg of this right triangle. The base of this triangle is what we're going to be interested in. And I sketch it here. You may imagine that that red line, which is the base width is the shadow cast on the negative x-axis. If a light were placed above this vector, a shadow indicated there in red would be formed. You may visualize that that arrow cast a shadow, also an arrow that points in the negative x direction. Consequently, the rule we use is that we attach a negative sign to the base width in order to determine the x component of a vector in the second quadrant. And so, using SOHCAHTOA, we see once again that the base width is the side of the right triangle adjacent to the angle theta, as opposed to being opposite. And so once again, it's a cosine term that's operational. And we have the following expression for the x component of b. We put a negative sign in front of the base width to indicate that the projection or component points in the negative x direction. And so here's your hypotenuse, and then once again the cosine term. And so you learn something important about x components of vectors, at least for the first two quadrants. If the arrow or vector points to the right in the positive x direction, which is the case here, the x component is a positive quantity. A is the length of the vector. Lengths of vectors are always positive. And the angle here, theta, is less than 90 degrees. And so you may recall from trigonometry that the cosine of an angle less than 90 degrees is positive. So we have positive times positive. We have the same here, positive times positive, but the negative sign makes the overall term a negative value. So the rule that you could use is this. If a vector leans to the right or is tilted to the right, as is shown here, then the x component is positive. There are two other quadrants we're going to look at, and you will see that in the fourth quadrant, the vector itself will likewise point to the right. So in the first and fourth quadrants, you will see when we're done, the x component is positive. Whereas for the second and third, this being the second quadrant, the third I'll draw soon, the x component is negative. Well, now we have a description of the x components of a vector in the third quadrant, and then in the fourth quadrant. Let's go back up to the third quadrant. We have a vector c that points into the third quadrant. As we did before, we drop a line down to create a right triangle. The leg height is shown there, but this video lecture is not about the leg heights. We're talking in terms of, or about, the base widths, which are plus or minus the x component of the vector. You can imagine that there's a light underneath this vector c that casts a shadow, shown in red, that is along the negative x side of the coordinate axes. As a consequence, according to our rule, which I'm describing to you now, we place a negative sign in front of the base width. Now the base width is found using SOHCAHTOA. The side in question is adjacent to the angle theta, so we use the cosine trig function. Hypotenuse times cosine theta, c times cos theta with a negative sign gives you the x component of the c vector. I've drawn a vector d that points into the fourth quadrant. It makes an angle theta with respect to the x-axis. Like as I did with the other three vectors, I created a right triangle, dropping a line down or up to create a 90-degree angle. We see the leg height, not of interest to us right now, and the base width. You may imagine there's a light underneath this vector that casts a shadow along the positive x-axis. The length or width of the base is found using SOHCAHTOA again. It's hypotenuse cos theta, d cos theta, and there's no negative sign because, well, this component's positive because the shadow is cast along the positive x-axis. Make sure you understand the rules for determining the x component of a vector very, very well. There's probably no other skill that's more highly valued in Physics 23 than the method of vector addition using components, a procedure I'll describe to you in a different lecture. But for now, you're learning only about determining the x components of a vector. In the next video lecture, I will show 4 similar diagrams, but we will then be talking about the leg heights, leg height, leg height, the leg of our right triangle. Those heights will be the focus of our attention. Some of those leg heights can be imagined to be shadows cast by a light directed toward the arrow along the positive y-axis, and then other vectors will have shadows cast along the negative y-axis. We'll save that discussion in detail for the next video lecture.